In the last couple of videos, we discussed Newton's laws. We first learned about Newton's first law, or the law of inertia. Let's recall that inertia is an object's resistance to change, and that mass is a measure of inertia. Okay, so therefore, inertia is dependent only on the object's mass. Now, what about when the object is moving? So there are two things that we want to consider: the object's mass and its velocity. And how we measure that is momentum. So momentum is mass times velocity. Momentum is essentially inertia in motion. This can also be written as P, which is a symbol for momentum, equals mass times velocity. Okay, and we see that momentum is a vector because velocity is a vector and mass is a scalar. So scalar times a vector is still a vector. So that means that momentum is dependent on both magnitude and direction. Just like, acceleration, velocity, and force are all vectors. Okay, we also see from this relationship that to change momentum, I can either change the mass or I can change the velocity or both. If I increase the mass, I increase the momentum. If I increase the velocity, I increase the momentum. And if I decrease either one of those, I also decrease the momentum. Momentum is measured in something called a Newton second. And that's Newton's time seconds. So we can find that by looking at how we find momentum. So we know that momentum is mass times velocity. Mass is measured in kilograms. Velocity is measured in meters per second. Okay. A Newton is a kilogram metered over second squared times seconds. These seconds cancel, and I'm left with kilograms meters over seconds. So the units for momentum are Newton seconds. You could write this one, but Newton seconds is just shorter and what you'll typically see. So let's say that I want to change my momentum. So there's two ways I can do this. I can either change the mass or I can change the velocity. Let's say that I'm looking to change the velocity. Let's say mass is constant. Well, to change velocity, I need to accelerate, right? And in order to accelerate, I need to apply a force. We know that acceleration is equal to force divided by mass. So if the mass is constant, I need to either exert a push or a pull. So the amount of force I apply will affect how much I accelerate, which affects my velocity. But there's a second factor. Also, the duration that I apply the force, the length of time that I push or pull, affects my acceleration, which then affects my velocity, which affects the momentum. So, if I apply a force for a longer time, I increase acceleration. If I increase acceleration, I increase my velocity. And if I increase velocity, I increase momentum. If I apply a force for a shorter time, the opposite happens. So, we see that two factors are important when changing momentum: force and time. And we call change in momentum impulse. So I'm going to put that on the next page. So change in momentum, remember that momentum, symbolized with a P, equals mass times velocity. So change in momentum is called an impulse. And how momentum changes is dependent on two things: force and time. So delta T, change in time. If we do a quick unit check, we see that the units for impulse are the same as the units for momentum. Remember that force is measured in newtons and time is measured in seconds. So impulse is measured in a Newton second. And if we look back, right here, momentum is also measured in a unit second. So we see from this relationship that if I increase the force, I increase my impulse or change in momentum, or if I increase the time I apply the force, then I also increase the impulse or my change in momentum. Okay, or I could do a mix of both. So let's now consider a couple real-world examples. Okay. Let's say I'm driving a car and I need to crash. Would it be a good idea for me to crash into this wall or into this fluffy pile of cotton balls? Alright, well, intuitively, you're probably going to say the cotton balls. Now, in terms of momentum and impulse, let's consider what's going on. Okay, so we know that impulse, which is just a capital I, is equal to a force times change in time. And we also know that impulse is equal to change in momentum, which is also equal to change in mass times velocity. It's important to note in these two examples that my momentum is decreased by the same impulse. What that means is that before I hit either one, the wall or the cotton balls, my initial velocity is the same, and after I hit the wall or the cotton balls, my final velocity is going to be 0. So my change in momentum is the same in both scenarios. So my impulse is the same in both scenarios. Okay, so if I hit the wall, my impact time, the time it takes me to go from my initial velocity to a velocity of 0, is very short. It's a very, abrupt stop. Well, if I hit the cotton balls, my impact time is sort of drawn out. It takes me a while to slow down to 0 velocity. So now looking at the equation, remember that I equals force times delta t. If my impact time is small, like in the case of the wall, then my force must be pretty large. So if I hit the wall, my impact force is going to be really large, and that's sort of dangerous. Now, if I hit the cotton balls, my impact time is large. Takes a long time for me to slow down. Therefore, my force is small, or I experience a smaller force. So it's better for me to hit the cotton balls than for it is to hit the wall. This idea can be extrapolated even further to explain why you bend your knees when you jump from an elevated position. So when you bend your knees, you're increasing the amount of time it takes for your velocity to go from whatever your initial velocity was to a velocity of 0, for you to be still. This is called your impact time. When you increase your impact time, you decrease the force, given that the impulse is constant. And it is because we're trying to go from an initial velocity to 0 velocity, so your impulse is the same. If you keep your knees rigid, if you don't bend them, then you decrease your impact time, therefore increasing the force. That force is felt in your bones, and that's why it hurts more to jump with your knees rigid than with your knees bent. Let's consider another example. What about, why do people, when they swing a bat, want to follow through? So, if, say, my arms are only so strong and I can only apply a certain force on the ball, the next best way for me to increase my momentum or increase the velocity of the ball is to increase my impact time. By following through, I increase the impact time, therefore increasing my impulse, which increases my momentum, which means that my velocity increases. All of these concepts can be used to explain things that you see every day, such as why does a glass dish break when you drop it on concrete versus when you drop it on a carpet? Why is it safe to fall in a safety net versus on hardwood floor? why does a bungee jump work? All of these can be explained by momentum and impulse. So now let's use this idea to consider how bouncing works. Okay, so let's say that I drop a ball and it doesn't bounce, it just hits the ground. For that to happen, the floor must provide an impulse to stop the ball. So that means that the ball has some initial velocity, and that velocity is now 0. The ball is at rest. Now, for the ball to bounce, the floor must stop the ball, and then now throw the ball back up into the air. Okay, so it takes more force, or more of an impulse, to stop the ball and throw it back up in the air than it takes to just stop the ball. Therefore, for the bouncing ball, the total impulse must be equal to the impulse to reduce the momentum to 0, plus the impulse to throw the ball back into the air. This overall requires more force to bounce a ball than it is to just stop the ball. You might have noticed that when you bounce a ball, it never quite bounces up to the height at which you dropped it. In the next video, we're going to talk about conservation of momentum and what happens during collisions and bouncing.